Distinctness of image, DOI, loss, and haze after bake are among the most subtle yet critical appearance defects in solvent-borne automotive coatings. While panels may pass standard gloss measurements, they can fail OEM visual approval if reflections appear soft, blurred, or cloudy. From an RD&I perspective, these defects are not random. They are a direct consequence of surface microtopography, pigment alignment, and film formation dynamics during flash-off and curing. Achieving high DOI and low haze requires precise control over multiple variables, including film thickness, solvent balance, rheology, flash-off, and environmental conditions. Unlike orange peel or stippling, DOI and haze affect optical clarity at a microscopic scale and demand both instrumental and visual verification in OEM production. Visually, DOI loss manifests as a softening of reflected images on the panel surface. For example, straight lines or lights may appear distorted, diffuse, or fuzzy, particularly when observed at low angles. Haze refers to a thin, translucent veil over the surface that scatters light, reducing sharpness and contrast of reflections. Under magnification, the surface exhibits microscopic unevenness, slight ripples, or fine texture irregularities. These irregularities often correlate with variations in pigment orientation, binder distribution, or microcavities formed during solvent escape. Pearlescent and metallic systems are particularly sensitive, as their optical effect relies on precise light reflection and interference. Even minor micro-roughness can produce noticeable haze or DOI reduction. The primary mechanism behind DOI loss is inconsistent surface micro-smoothness. Metallic flakes must lie parallel to the substrate for uniform reflection, while binder and pigment distribution must be continuous and level. Surface irregularities, caused by early skin formation, trap solvents, or uneven flow, disrupt the specular reflection path, causing reflections to appear diffused. Haze arises when microscale air pockets, solvent bubbles, or minor surfactant residues scatter light, reducing clarity. Both defects are heavily influenced by flash-off timing and solvent volatility. If the flash-off is too short, rapid skinning traps microbubbles or prevents pigments from settling, creating a rough microtopography. If flash-off is excessive, surface flow may induce localized sag or flake tilting, which can also reduce DOI. Film build is another critical factor. Excessive DFT increases the diffusion path for residual solvents and amplifies microscale surface tension gradients, which distort pigment orientation. Very thin films may not provide enough binder matrix to fully support flake alignment, leading to localized optical inconsistencies. OEM plants routinely measure DFT across critical areas and use target ranges specified in TDS to minimize DOI and haze issues, balancing optical performance with mechanical protection. Even minor deviations across edges, curves, or horizontal surfaces can lead to observable differences in reflection quality. Viscosity and flow behavior of the base coat are directly linked to DOI and haze. High viscosity systems resist flow, locking pigments in non-optimal positions and reducing leveling, while low viscosity systems may sag, causing microwaves or localized pooling. Flow and leveling additives improve pigment mobility and surface smoothness, allowing metallic or pearlescent flakes to align parallel to the substrate during flash-off. Anti-settling agents prevent pigment flocculation, ensuring even distribution during spraying. However, overuse of additives can increase viscosity or surface tension gradients, producing secondary defects like cratering or orange peel, which indirectly worsen DOI and haze. Environmental conditions in the spray booth, including temperature, airflow, and relative humidity, play a subtle but significant role. High temperature accelerates solvent evaporation, shortening the open time and potentially trapping microbubbles or pigment misalignment. Low temperature or high humidity slows evaporation, allowing pigments to settle properly, but increasing the risk of sag or surface contamination. OEM plants carefully control these parameters, often performing test panels under simulated production conditions to define robust process windows. Spray mechanics and application technique are equally important. Gun distance, traverse speed, atomization pressure, and overlap percentage influence pigment laydown uniformity. Variations in spray pattern or panel orientation can create localized micro-roughness, reducing DOI in specific zones. Multi-layer systems introduce additional complexity. Interactions between primer, surfacer, and base coat layers affect pigment distribution and binder flow. Uneven surface energy or residual stress from underlying layers can propagate into the top coat, amplifying haze or DOI loss. OEM engineers use a combination of visual inspection, multi-angle DOI meters, and haze instruments to detect and quantify these defects accurately. Troubleshooting DOI loss and haze requires a systematic approach. First, inspect the panel under both directional and diffuse lighting to identify affected zones. Second, correlate these zones with DFT mapping, flash-off logs, and oven ramp profiles to detect process inconsistencies. Third, review viscosity, solvent blend, and additive selection to ensure pigments had adequate mobility without introducing secondary defects. Finally, verify spray parameters and environmental control. Only by integrating all these variables can OEM teams consistently achieve the required optical performance across complex geometries and multi-layer systems. The key takeaway is that DOI loss and haze are optical defects caused by microscale surface irregularities and pigment misalignment, not by gross formulation failure. Prevention depends on process discipline, optimized flash-off, controlled film thickness, environmental consistency, and judicious additive use. Corrective action after panels have been baked is limited. Minor haze may be reduced by polishing, but true DOI recovery requires process correction and reapplication. OEM plants that understand and control these variables achieve consistent visual approval, minimal rework, and predictable high-end appearance in metallic and pearlescent coatings. If you've experienced panels with soft reflections, haze, or inconsistent DOI despite correct gloss readings, leave your questions in the comments. Future episodes will continue exploring secondary and tertiary shade matching, color flop, and multi-layer optical interactions, providing practical OEM troubleshooting strategies for all visual appearance defects.